This is Microlecture 17 on alkane naming. Okay, so what we're going to be talking about here is the IUPAC nomenclature system. IUPAC stands for International Union of Pure and Applied Chemistry. And it's just a system of naming so that when we're looking at different compounds and we're communicating our discoveries with one another, we can be on the same page with just a name like 3-methylbutane, and we don't have to draw out the structure to convey what molecule we're talking about. So part of having a nomenclature system means that we have to have rules like, for example, how we number the carbon atoms in our structures. It's going to be in a very particular way. So you see in this example, we would number the 4 carbon atoms that are in the parent chain, which happens to be the longest continuous carbon-carbon chain. We would number them from left to right and not right to left. And we'll talk about why, and we'll go through all of these rules. But the longest continuous carbon-carbon chain is going to be the starting point. We're going to learn how to find it and how to number it. Anything hanging off of that is called a substituent. So any branching group is a substituent on the parent. And so let's talk about the different types of alkanes that there are. Alkanes are hydrocarbons containing only single carbon-carbon bonds. Okay, otherwise they'd be alkenes or alkynes. So within these singly bonded systems, they could be there could be linearity. So that's when we're just alternating up, down, kind of staggering the carbon atoms. So that would be a linear hydrocarbon. And then as soon as we have a substituent or a branching group like that. Or maybe something even more complicated. That branching group is called a substituent. This would be an example of a branched alkane. And then we have cyclic alkanes, so cyclic systems, and we've seen plenty of examples of these in our homework so far. Okay, so one thing that we'll have to learn how to do is refer to alkyl carbon atoms as being primary, secondary, tertiary, or quaternary. So it turns out that when you have a carbon atom that has essentially another carbon-containing group off of it, or a carbon atom off of it, we'll call it R for the rest of the molecule, because it really can be anything, and then 3 hydrogen atoms, this is going to be referred to as a primary carbon. A secondary carbon is one that has 2 R groups and 2 hydrogen atoms. And tertiary, you see the trend here, is where we have 3 R groups and a hydrogen atom. And then a quaternary carbon has no hydrogen atoms. It has just all R groups on it. Now typically we use this nomenclature system just for alkyl carbons. So I've included a big, hairy, scary looking molecule here, and it's got several alkyl carbons in it. Below it you see the IUPAC name, not to scare you, just to kind of be funny and comical. This is something that we would never name systematically in this course, but everything has an IUPAC name. Everything, even proteins. And sometimes you'll see t-shirts that are just filled from top to bottom with the name of one protein, for example. So I'm going to just number some carbon atoms here. I'm going to number them, and then you'll pause the video and tell me whether these carbon atoms that I'm numbering are primary, secondary, tertiary, or quaternary. So here we go. Let's pause the video at this point, and you can label them. So carbon number 1 is attached to 3 hydrogen atoms. So there's 1, 2, 3 bonds to hydrogen that are just assumed to be there, right? So because we've got 3 bonds to hydrogen, this is going to be a primary carbon. Carbon number 2 has 1 missing bond there. The other 3 are going to other carbon atoms within the molecule, and so that is going to be a tertiary carbon. Carbon number 3, we have actually a couple of understood hydrogen atoms there. So 2 hydrogen atoms and 2 carbon containing groups is going to make that a secondary carbon atom. Same with the one that I've labeled number 4. It has 2 understood hydrogens, and same with 5. It has 2 understood hydrogens. So these are all secondary carbon atoms. Okay, so the first part of naming is finding the longest continuous carbon-carbon chain. So remember, the parent is the longest continuous carbon-carbon chain. I'll give you a couple of examples here. So maybe this as an example to name, and then we'll name this one as well. Finding the longest continuous carbon-carbon chain means that once this molecule is drawn out for you, say on a piece of paper, you would be able to take a pencil and trace from one carbon, the beginning carbon, to the ending carbon without lifting up the pencil. That's how you find the longest continuous carbon-carbon chain. So we want to maximize the number of carbons in the parent chain. See if you can do that with these 2. Pause the video and then we'll come back. So the longest continuous carbon-carbon chain for the first one is going to be right here. And I actually could have traced that differently. I could have gone this way and it would result in the same IUPAC name for this molecule. The next one, 1, 2, 3, 4, 5, 6, oops. My highlighter didn't want to follow me. 1, 2, 3, 4, 5, 6, 7. So there's 7 carbon atoms in the longest continuous carbon-carbon chain there. Again, I could have wound around differently with that last one and gone this way, and it wouldn't change the IUPAC name at all. That's kind of why we find the longest continuous carbon-carbon chain. And then we go ahead and number each carbon atom. And the rule here is that we want the branches or substituents to have the lowest carbon number possible. Alright, so for that reason I'm going to call this carbon number 1 so that the branch can be on carbon number 2. And then I have 3, 4, and 5. I wouldn't number it any other way because that any other way would not give the branch the lowest carbon number possible. So go ahead and number the other one and pause the video. And so this one is going to be carbon 1, 2, 3, 4, 5, 6, and 7. And so now it's time to start naming our branching groups. So off to the side, let's just make a couple of notes here. Remember that we want the lowest number on the substituents. And another kind of side rule that doesn't come up very often is we want to have the a maximum number of substituents or branching groups. Right? So if there's ever a debate about what should be the parent name, because going one way you would have the same number of carbons as going the other way, then the way to sort of break that tie is to maximize the number of branching groups. We always want to maximize the number of branching groups. So again, that doesn't come up here, but it is a rule. All right, and so we have all these names in these tables that we can use and look up. The branch on carbon number 2 for the first compound here is a CH3, and so we know that a 1 carbon branch is a methyl group. So if we look at table 4.2, names of alkyl groups, 1 carbon is a methyl group. And so I would name this compound 2-methyl, and then without any spaces, all lowercase. So this should be comfortable for you if you're used to hashtags. It's going to be the parent name now, so that is going to be for a 5-carbon parent pentane. Okay, so 5-methylpentane is the name of the compound. The next one is we can look up the parent name straight away. So that's a 7-carbon parent, so that's going to be a heptane. And we always put the branches first. And the other thing is we list the branches in alphabetical order. So another side rule worth noting is that we name the branches in ABC order. Right, so for that reason I'm not going to put 2-methyl at the beginning because on carbon number 4 I have an ethyl, and that's a 2-carbon, so an ethyl, 2-carbon group. And ethyl starts with E. It comes before methyl. So the name then of this compound is going to be 4-ethyl -2-methyl, and the parent is heptane. So let me move this text out of the way. Sorry, the parent is, heptane, and so it's all one word, all lowercase. You're noticing that dashes are used to separate letters from numbers always, so we used it after the 4, and after the 2. That's how they're used specifically. Okay, so let's do another example. I don't have the tables on this slide to give me a little bit more room, but you can have them up on your screen and solve this one. See if I've decorated it enough. I think so. Alright, let's go ahead and try to name this compound using all the rules we've talked about so far. First, you want to find the longest continuous carbon-carbon chain. And I'm going to say that that's probably going to be right here. Let's count how many carbons we have in that longest continuous carbon-carbon chain. See what we have for a parent. So I'm getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this parent is actually a decane. Okay, and we have actually a couple of methyls on carbon 2. It looks like an ethyl on carbon 3, a methyl on carbon 7, and a methyl on carbon 8. Keep in mind that when you have a substituent that is the same, like methyl, we have a prefix for however many number of methyls. So for example, here on carbon 2 we have 2 methyls, a methyl on carbon 7 and a methyl on carbon 8, so that's 4 methyl groups. And 4 methyl groups would be tetramethyl. Right? So there's usually not more than tetra, and so if you have 3 groups, it's tri. If you have 2 groups, it's di. Alright, and we don't have to use anything when there's just 1 group. So with that in mind, the name of the compound, listing everything alphabetically, I'm seeing on carbon number 3 an ethyl, and then I'm seeing these 4 methyls that are on carbon 2 again, carbon 7 and carbon 8. The way we write that is 2, 2, 7, 8 dash tetramethyl. And that means we have 4 methyl groups, and they are on carbon 2, carbon 2, carbon 7, carbon 8. So that's all the substituents, and then all lowercase, all one word. We list that with the parent, which in this case is decane.